Hi, I'm Ashwin, and I'll be going through some of my contributions for the air conditioning system prototype project. So, I was mainly involved in implementing the rotary encoder, which is used for the fan speed control and turning on and off the whole system. And I was also involved in implementing USART transmissions via an interrupt. So, how a rotary encoder works is that we have two pins. We'll name this one DT and we'll name the other one clock. When we rotate clockwise, the DT pin goes high first and then quickly followed by the clock pin. And that's for one increment when we turn it once. If we turn it again, another increment, DT pin goes low first and then clock goes low. So it's like an oscillation. It keeps going, keeps repeating these two states as many times as you increment. Now, if we go anti-clockwise, we're going this way now. The clock pin goes high first and then the DT pin goes high. So based on just this information alone, we know which direction the rotary encoder went. If DT pin goes high first, it's clockwise. If DT pin goes low, if clock pin goes high first, then it's anti-clockwise. So we can implement a simple state machine that tracks these changes and tells us which direction the rotary encoder moves. So we start at start. That's when we haven't done anything yet, and we have 4 other states. And in our interrupts, we have 2 interrupts. We have the clock interrupt, which is connected to int0, the external interrupt, and our DT interrupt is in int1. So in the interrupts, we simply read both pins and we switch on the rotary state. So when we're at start, we know that we haven't touched the rotary encoder yet, and we haven't signaled a direction to move yet. So as soon as something happens and we're still only in the start state, we only say that we're intending to move anti-clockwise. We're not committing to anything yet. So now, why that's the reason is because if we take this if statement, for example, we say we're at start and DT goes high. This is the DT interrupt after all. So this goes on a pin change. The interrupt triggers on a pin change, and then we think that, okay, the if statement triggers and DT is high. So we're probably at this point right here. Now we know that one increment is both DT going high and clock going high. So we need to wait for clock to go high as well. So at this point, we can't say we're going anti-clockwise just yet. We need to say we're intending to go anti-clockwise, and only when clock goes high as well, which is down here, clock goes high according to this if statement, and we're in the case intent anti-clockwise. So now we know, okay, for sure we're going anti-clockwise. So that's how the state machine works, and it's a similar story for intending to go clockwise and going clockwise actually as well. Now, with just this information, now that we know the states, we know that when the rotary state is clockwise, we can just simply increment motor duty, and when state is anti-clockwise, decrement, and just set the rotary state back to start. So pretty simple there. So that's how the rotary encoder works in the code. And in this demo, you can see my duty cycle. If I go anti-clockwise and decrement it once, we see that duty goes lower by 0.5, and we see that in the top graph, we get a change in DT and clock. Similarly, if we keep going, we can see that it caps off at 0.95 as it's a duty cycle, but as we keep decrementing or incrementing, the duty cycle changes accordingly. So that's how the rotary encoder works. The other thing I was also involved with was the USART transmission using an interrupt. So our USART interrupt vector is very simple. This USART UDRE simply is triggered when the shift register is ready to be written to again, meaning we're ready to transmit another byte through USART. So basically what happens in this interrupt is very simple. We simply check if our USART buffer is not empty, and if it's not empty, pop 1 byte out of the buffer and set it to UDR0, which is the shift register. Basically transmit that byte. Now what the USART queue is a first in first out queue. It's a basic data structure. What a first in first out queue is it's simply an array, but you can only add elements at the end of the queue and only remove elements at the start of the queue. So what this does is it ensures that we transmit data in the same order that we sent it through. So this is obviously important for USART because we can only transmit 1 byte at a time, and we want to make sure that we transmit the bytes in the correct order. So how I've implemented the queue is simple. Queue init just sets the capacity, the head, and the tail. And in our enqueue adds one element to the queue at the back, and dequeue pops one from the front. We simply adjust the tail and the head accordingly and mod it by queue capacity so that it doesn't go out of bounds. So pretty simple. And then if we want to enqueue a string, we simply call enqueue in a while loop for all the characters in the string. Similarly, for a float, we convert it to a string first and then enqueue string the float string. So that's how our USART transmission works, and I can show you in the code. We simply call enqueue string on whatever we want to transmit. So it's that simple. So my parts were mainly related to using interrupts to make our life easier. So you can see here what an interrupt is basically you have your regular program flow, but some incident happens and that triggers an interrupt. It could be an external interrupt, it could be a pin change interrupt, it could be the USART transmission interrupts, but that interrupt occurs and it breaks the normal flow of the program, and it goes into your interrupt service routine and executes code what you specify in your interrupt service vector. So this stuff runs, and then we go back to the program counter and we go resume normal operations. So this makes our life easier because it can be very useful in like real-time settings. So say like you're doing some long task, but you need to handle that button press now immediately because maybe the button is the brake of your car, and you want obviously the brake of your car to be very responsive, so you can't have any delay on that. So an interrupt is useful there because it's the more important task. So that's a little bit why interrupts are important and how they helped us in our project as well. Thank you.